Section 2.5 is called the chain rule. And in this section, what we have is we have what's called a composite function. You may have seen somewhere this notation written in an algebra course or something like that, where it looks like fog. All right, it looks like there's a little zero. It's tiny, though, in between the f and the g. And it's defined as one function, that is the g of x function, because it's listed second, inside of the f of x function. So whenever I see these composite functions, they look like something inside of something else. It always looks like something inside of something else. What you'll notice when we do the derivative here is that you do the derivative of the outside piece, which is the f of x function. So you see f prime. But what do you see written inside right here? Just g of x, exactly like it was before. So the inside didn't change. Okay? So when I did the derivative on the outside, I left the inside untouched. And then I multiply this by the derivative of whatever was inside. So we end up taking two separate derivatives. The first piece that we take, though, has the inside rewritten as it is. Now, sometimes it's hard to see the inside function if you're not accustomed to it. So that's going to be the first thing we're going to do as we look at them. We're going to look at them and say, oh, I know what the inside is, and then I know what the outside is. Because if we can identify the inside and the outside, the derivatives are not usually the problem. It's usually the identification that causes people concern. So let's take a look. Now this particular problem looks like something is inside of something else. A lot of times that inside feature will be inside of a set of parentheses, which is actually quite helpful. So what is the inside function here? Yeah, this piece right here is inside. The outside is the power 5 and the 2 at the front. Those pieces are what's going on the outside. So I want you to think about what I've drawn in blue as though it's just this big blob. You don't know what it is, it's just a blob. So you've got 2 times blob raised to the 5. Okay? So we're going to deal with that part that I said without sort of ignoring the part that's in blue for the moment. If you had a 5 exponent, what would you do with a problem? Right, you bring the 5 down and you multiply. So that's going to be 2 times 5 is 10. And then you would decrease the exponent by 1 to give you a 4. That's the derivative of the outside. You brought the 5 down, multiplied it by the 2, and then you reduced the 5 to a 4 exponent. And then the stuff inside, the blob, the blue part, all gets rewritten exactly where it was before. It is unchanged. Then you can multiply by the derivative of what's inside. So what is the derivative of 6 minus x squared? Perfect. That's the chain rule. And if you were doing the derivative quiz, you would stop there. But you're not today, right? So we're going to go one step further and simplify this. Now, the part that's raised to the 4th power, that doesn't have the ability to combine with the other pieces, but these two pieces certainly have the ability to combine together. So we're going to combine the 10 and the negative 2x to give me what? Right. Negative 20x, and then that will be multiplied by 6 minus x squared to the 4th. So this would be my derivative.
Why did you not mess with the 6 minus x squared?
That's part of the chain rule. The chain rule says that when we take the derivative, we leave the inside of the outside, we leave the inside untouched. And then afterwards, we multiply by the derivative of the inside. So we do take the derivative of the inside, just not while it's currently inside of the outside function. It's a separate piece. Okay. All right, let's try another one. This one looks a little bit like it should be a quotient rule. The reason it's not really a quotient rule is because the numerator doesn't have any x's in it. So if you use the quotient rule, you'd get the right answer. It would just be a little bit weird because part of your derivative would give you the derivative of the top, which would be 0. So it's just a little bit funny to think about it that way. It's a little more natural to think about it as a chain rule, although if you look at it right now, it doesn't look like there's anything inside of something else. However, I can rewrite it so that it does look like that. going to take the denominator, I'm going to pull it up to the numerator. When I do that, it makes the whole denominator as the whole have a power of -1. Whole thing has a power of -1. Okay, pretty good so far with the rewriting step. Excellent. So the inside now is actually inside a set of parentheses, just like on the last one. So we're going to take the derivative. So what will the derivative of the outside be? Right. So I bring my -1 down. I have the piece of parentheses that I'm leaving sort of empty at the moment. And then I decrease my exponent by 1. Good job, Stephen. Okay, does that look okay to everybody? Make sense? The piece that's in the middle now is going to be rewritten. Okay? So this is the x squared plus 3x minus 1. Now we are going to do the derivative of the inside. So what is the derivative of what's inside? 2x plus 3. Does that look okay to everybody? Excellent. Now, just like on the last problem, there's pieces of this that combine nicely. The piece that has the -2 exponent, where do you think we're going to do with it?
Put it on the bottom.
We're going to put it back on the bottom. That's where it started, right? Having that negative exponent rewritten as a positive exponent means putting it back into the denominator. But now it will be squared in the denominator. What will the numerator be? Good. -2x minus 3, though, I think, right? Yeah? You see that denominator squared? If we'd done the quotient rule, we would have gotten a denominator squared, wouldn't we? That's not a big surprise that that's coming out in this particular interpretation of this particular problem. Any questions on this one? Okay, let's try another. This one is definitely more complicated than either of the ones we've done before. We worked on ones before that were not near as messy. Yes, you do. All right, so Luke saw something fun, and he just noted it. First, we will talk about the chain rule. Do you see something inside of something else? What's inside? The fractions inside. The fractions inside of a square root. You can also think of writing this, in fact, we're going to want to later anyway. You can think of writing this like this. Right? Once you see those parentheses, there's no question in your mind. All of this is the inside function. All of that right there. So let's start with that piece. What is the derivative of the 1/2 power business? What do I do? Pull the 1/2 down, and I have a -1/2 power. Everybody good with that piece? Yes, Luke?
So, I think I went about it the harder way, but would this also work? I divided the...
Yes, you can do it that way.
Up and then did a quotient rule with the product rule, or chain rule.
Yeah.
Yeah, that's awesome.
Yep, you can do that too.
It is cool.
I think it ends up being a little bit longer to do it that way. It's not a problem, but yeah, you can do. You will find when we're working with something that's got a quotient and a chain, or a product and a chain involved in the same problem, there's often more than one way you could work it. Yeah.
The worst part about this problem is that it's T.
So sorry, Will. All right, this is 3t minus 2 and over 2t plus 3. All right, I do need the derivative of the inside now, and the inside is a quotient. So I've got a quotient rule now in the middle of doing this chain rule. Not really in the middle, at the end of doing this chain rule problem. So I've got a quotient, and so I'll do the easy part. 2t plus 3 is the denominator, squared. So we just got through doing a quotient rule just a few minutes ago. So somebody tell me what will come first when I do the quotient rule for this particular numerator.
Regular.
The denominator. The regular denominator, yes. And then what? What's the derivative of the top? What? 3. The 3 is the derivative of the top, right? What's wrong?
Wait,
It should be 2t squared.
Oh, did I leave a squared off somewhere? I sure did. Thank you. I left it off all the way along. Let me fix that. Okay, so what would it be then? 6t. Thank you. Yeah. All right. Now I need what? The numerator. So that's the 3t squared minus 2. Times the denominator. What's that piece going to be?
2.
Just 2. Now more than ever before, you wish you were doing the derivative quiz, don't you?
Yeah.
Yeah. Because I have to simplify this at this point now, but next Tuesday I won't have to, nor will you. So let's see what we can do. Let me tell you, comment first that we've got this power -1/2 here, and I want positive powers when I'm done with things anyway. So if I flip this upside down, I will have a positive power, right? So I'm just going to take what's there as a fraction. I'm going to flip it upside down with 1/2 power. So this will be 2t plus 3 over 3t squared minus 2. And this is a power of 1/2. And even later, I probably will be distributing that 1/2, kind of like what you were asking, Luke, when you said, could I just distribute the 1/2 to begin with? I'm going to distribute here in a minute later when I'm simplifying, and that will help us. Yes?
What you just did.
Okay. A negative power can be changed to positive if I flip a fraction upside down. So like if you had 1/2 to the -2, this would be the same thing as having 2 over 1 to the +2. You can flip it upside down, and it changes the exponent from positive to negative. We use it all the time, but we basically were using bringing it to the numerator and moving a numerator to the denominator. We're just doing it in the same step.
Okay, so you wouldn't just immediately multiply the 1/2 by 1. Never mind.
Yeah, we can't multiply by the 1/2 either because it's an exponent of 1/2. So because of that exponent, we're not going to be able to simplify the 1/2 in the front or the exponent of 1/2 at the moment. We will see something simplify in a minute, but not what you're expecting right now.
I don't like this one.
I know, I'm sorry. You don't have to like all of them. All right, how about the next piece, though? The next piece is kind of a mess. Part of the next piece has a denominator that's 2t plus 3 squared. And you might notice, I'm going to highlight it so you can see. Do you see this 2t plus 3 in the numerator? And I've got a 2t plus 3 in the denominator. They don't have the same exponent. They definitely match, right? We're going to have to make concessions to that in a little bit. Those are going to be combined in some way. We're not doing that now, but we will have to later. We need to simplify that numerator right now, though. So somebody tell me what I'm going to have in my numerator.
6t squared.
How about 12t?
Oh, yeah.
12t squared, uh-huh.
Plus 18t
Good.
minus 6t squared. Plus 4.
Okay, does everybody agree? And the 12t squared and the -6t squared, those two pieces will combine. Agreed? All right, just so that I have it already here, I'm going to go ahead and write these as 1/2s individually because I'm going to need them in a minute anyway. All right, that numerator now becomes 6t squared, I think, yeah? Plus 18t plus 4. There are two things that simplify. One of them I've already mentioned. Do you see the other one? It's the easier simplify. The one other thing that will simplify. Okay. The 1/2 here in the front can simplify with this piece right here. Okay. I'll rewrite it so I'll move it around so you can see that a little bit cleaner. So I'm just going to combine this all into one fraction because that's what you can do with fractions when they're being multiplied, is you can combine them all into the same expression. This is 2t plus 3 to the 1/2 over 3t squared minus 2 to the 1/2 times 2t plus 3 to the 2 times 6t squared plus 18t plus 4 And I'm going to put the 2 here at the back so that you can see it simplify in a minute. Now, first of all, there's 2 questions sort of inherent in what you just asked. Why did I do it, which is the answer I just answered. Now, and the why am I able to do it? I'm able to do it because this is multiplication. The order of multiplication doesn't matter. What's that? Yes, that's exactly right, Noah. All right, so let me give myself some more space here, just a moment. Okay, so Noah noticed that on the numerator here, this piece, I think is what you're saying, Noah, right? They all have a 2 in them. Do you guys see that? So I'm going to factor a 2 out of that numerator. Now there's a 2 on top and a 2 on bottom, right? Does everybody see the 2 on the top and the 2 on the bottom? If you recognize it, you could, from here, simply reduce each of these by a power or a factor of 2. And that would be fine as well. Or you can recognize it like Noah did, which is the actual factor coming out, which is the reality of what we're doing when we do that reducing. The other thing is this has a power of 2 and this has a power of 1/2, right? So this is the equivalent to having something like, oops. Let me use a for a moment just so I don't use the same variables. A to the 1/2 over a squared. So this is actually the same as having what? 1 over 8 of what power? Remember? 3/2. This is a property of exponents. You can subtract the powers. 1/2 minus 2 would be negative 3/2. Negative 3/2 in the denominator would be positive 3/2. Yes, Tammy?
I still don't, like, it's the 1/2 that's given to me. Like, because you flipped at the beginning so it's not negative, and then you flipped it again.
You mean this right here?
Yeah, like, I understood when you flipped
Uh-huh.
it and then made it positive.
Right.
But then,
There's another 1/2 in the problem that I'm working with at the moment. That's nothing to do with the exponent at this point. It's just a coefficient in front. The 1/2 in front's a coefficient, so when I'm working with it over here, I'm writing it as a 2 in the denominator because 1 over 2 puts a 2 in the denominator. Okay? All right, so the last piece, almost done with the problem. I know you guys are weary of this particular problem, so am I. Is that I have 3t squared plus 9t plus 2 on top. On the bottom, I have the 3t squared minus 2 to the 1/2, and then I've got 2t plus 3 to the 3/2.
Can you FOIL those?
Yeah, how did you just, how'd you get that on top? Where'd your 2t plus 3 do?
It's right there. Because that's what I did over here, guys. We just went through it. It's okay. I took a little interim there to have a different question. So this power to the 1/2, and this is, oops, this power to the 2, they combine because they're the same factor, 2t plus 3. Power of 1/2 on top, power of 2 on the bottom, they can combine. So they're a power of 3/2 in the bottom. It's a property of exponents. This right here is the same as a to the negative 3/2, because 1/2 minus 2 would be negative 3/2, which is the same as having the 3/2 in the denominator in the bottom. You guys just thought you remembered your algebra. This was algebra intensive, correct? A lot of algebra in there. Oh, come now. Come now, come now. Have a happy attitude. All right.
So that's it?
That's it. That's our answer. Lovely, right?
Oh, so you can't FOIL those even though the power would equal 1 in the end?
No, because one has a power of 1/2 and the other has a power of 3/2. If they both had a power of 1/2, like they matched, yeah, you could combine them. I don't know that it would be helpful to do so on the particular problem, but yes, it would be possible to do so.
Wait, can you combine them even with
Yes, you could write it all out to some extent, but the combining wouldn't be simply combining 3t squared minus 2 times 2t plus 3 and then rewriting a power. You'd actually have to write out like, so let me answer your question. We're not going to do this, but let me answer your question. This is the same thing as having this, right? And the power of 3 halves is the same thing as having 2t plus 3 and a 2t plus 3 underneath a radical. So in some sense, these two could be combined because they're both underneath a radical, but they wouldn't combine with this one at all because it's not underneath. But it doesn't simplify the problem any to do that. You're just making a bigger mess at that point. So we will leave it in factored form, which is with the powers of the 1/2. Okay? You guys are asking good questions. Thank you. Oops. You can do either one. Either would be fine. Yeah. All right. Oh, goodness. I haven't even defined this yet, but I bet you could guess what it might be. This says find the second derivative of the function. What do you suppose a second derivative is? Yeah. You find the derivative and then you do it again. It's the derivative of the derivative. All righty, you guys, good job. All right, so this will be rewritten the same way we just did the problems before with the power of 1/2, right? Very nice. So this is a chain rule. Do you see something inside of something else? What's inside? You betcha. All right, so let's do the outside part. What is the derivative of this raised to the power of 1/2? Perfect. And then I need the derivative of the inside. So what's the derivative of the x squared plus 4 part? That's 2x. Can you combine something? Yeah? The 1/2 and the 2x. How will those combine?
1x.
Yeah, just 1x or x. Now, I could, if I were finishing the problem, rewrite this with the negative 1/2 down in the denominator as a square root and so forth. That wouldn't especially be helpful, though, because I'm not done with my problem, right? I'm sort of in an intermediate step. I was actually asked to find the second derivative. Now, notation looks like this. You put a double prime. If you were doing a dy dx, remember we talked about this notation last time as being the derivative? The second derivative looks like dy, sorry, get it right, d2y over dx2. It looks like this. This is read as the second derivative of y with respect to x twice. Okay? I'm not asking you to use it, but I do want you to know that if you see it, that's the same thing as the second derivative notation with the double primes. Okay? So we're going to do the second derivative now. But you should notice that this is different than when we did the first derivative. What's different? How is that going to change things? You have a product now. Do you see it? Aaron. It's not that bad, I promise. Do you see a product? I have an x at the beginning, and it's multiplied by something else. Now, a product is only going to be, it's only going to be a product if I have two things with x in it. And I do. I have x, and then I have this function over here that's got x in it as well. So I have two pieces of something multiplied, each of them having x in it. All right? So for instance, some people like to say, let me give you back to the one that we started with over here. Some people would say, or would try to say that this is a product rule. It's not a product rule because I don't have a piece that's times x on the outside. I don't have an x on the outside of this. So I have a coefficient that's a 2, so there is multiplication going on, but it's not a product of two pieces with x in it. The one that we're working with right now, it is. I've got a piece with x in it, and it's just plain old x on this one, and I've got a piece over here with x in it. So the product rule says I'm going to rewrite the first piece, or at least that's the way I do it. And then I need the derivative of the second piece. That is, I need the derivative of the x squared plus 4 to the negative 1/2, and that is a chain rule, isn't it? So have a product with a chain inside. All right. Chain rule. It will become better the more you do, I promise. Chain rule. What do I do? I put the exponent in the front, and then I decrease my exponent by 1, right? What's my new exponent going to be? Good. And then the inside is going to be rewritten. It's exactly the same. And then I'll multiply by the derivative of the inside. So what's the derivative of the inside? 2x. We already did that once, didn't we? It's a product, so product will have a plus sign. The product rule. The other piece of this is very easy. Okay? The other piece of this is to take the derivative of the first piece. What's the derivative of x? 1. And then rewrite the second piece, which is the x squared plus 4 to the negative 1/2. We're going to combine and simplify this. It actually simplifies down quite a bit. Obviously, you know you can combine this negative 1/2, this 2x, and this 1. I'm not marking them out. I'm just highlighting them. Okay? All three of those pieces can be combined. So when I do that, I'm going to get negative, obviously. This 2 actually does reduce, right? I've got a 1/2 and I've got a 2. So I'm going to get x squared, and it's negative x squared. Because my exponent's negative, I'm going to go ahead and put it in the denominator. So this is x squared plus 4 to the 3/2. Plus, the other piece is just 1 over the x squared plus 4. But that x squared plus 4 is raised to the 1/2. It already looks considerably better, agreed? Don't have any negative exponents. I do have powers of 1/2 involved. The powers don't match, but they could. And they could because I could multiply the numerator by x squared plus 4 and the denominator by x squared plus 4. How would that help? Well, this has a power of 1. The part that's in purple has a power of 1/2. What is 1/2 and the 1 going to be then? 3/2, which means it'll match the other piece. Do you guys see that okay? You have to remember that 3/2 is simply 1 and 1/2. I already have the 1/2, right? This piece here, this is 1 and 1/2. I already have the power of the 1/2 here, so I needed the power of the 1 here to match. So I can get a common denominator by multiplying by x squared plus 4. But of course, if I do that to the denominator, I have to do it to the numerator. So this ends up giving me negative x squared on top. I have x squared plus 4 to the 3/2 on bottom. And then over here, I've got plus x squared and plus 4. So what does this this numerator become? 4. So the second derivative is 4 over x squared plus 4 to the 3/2.
It was about just as complicated to have like, whatever you were saying, that was like a second or elementary step or whatever that you left, like unsimplified after you got the first derivative.
This piece right here.
Yeah.
Yeah.
Yeah, I like put that on the bottom and did a quotient rule. And
You
it
could.
was just
About the same number of steps.
You didn't have to multiply by
That's
that,
true.
but it was about just complicated.
Yep. Yeah, there's often more than one option. There really is often more than one option on how to finish solving a problem.
But
Or
I
to
don't
even
think I
solve.
would have seen to multiply by that, just because I've never done it that way.
Okay, so did you guys hear Will's suggestion or what he did? I think it's a good option too. You could write this as x over x squared plus 4 to the 1/2, like this. And then using that, you could actually use the quotient rule, which would be fine. Now, your quotient rule is still going to have a chain involved, isn't it? Because your denominator still has something inside of something else. So you can't avoid the chain part of it, but you can do it as a quotient instead of as a product. Okay. All right, there's one more problem in this section. Compute the derivative for h of x equals f of g of x. And then instead of giving you any kind of equation, they give you a whole bunch of numbers, don't they? This problem's pretty straightforward, but it's not anything we've seen happen before, so I want to walk you through it very carefully. They want you to evaluate a derivative at the point 1. And your function that they're giving you is f of g of x. So by definition, or by the rule, or by the property, however you want to think about this, it's actually more of a theorem than anything else, we know how to find the derivative of a chain. It's actually the chain rule. I mean, it's written out. It says we should take f prime, we should rewrite the g of x inside, and then we should do g prime of x. That's the chain rule. Flat out, all I did was rewrite the rule. So far, so good? But this problem doesn't ask me what h prime of x is. It asks me what h prime of 1 is. So what do? We're not finding any more derivatives. What do I do?
Plug in numbers.
We plug in numbers? What number am I plugging in right now? Say it for me. A 1. Where? For the x. All right? All that's done here is that this x turned into a 1, which means on the other side all the x's have to turn into 1s as well. That's all this is. X's become 1s. F prime of g of 1, g prime of 1. From this part right here, I know what g of 1 is, and I know what g prime of 1 is. We'll do one of them at a time just so that we're not getting confused in the mix. What in the world is g of 1? 2. It was given to us right here. Agreed? What is f prime of 2? Because that's the next piece I'm going to work with right here. It's 3. And what is g prime of 1? Oops, sorry, the right one. It's -2. So this is -6. They do give you a lot of unneeded numbers. There's a couple reasons for that. Number one, usually a direction set like this will ask you for several things. Like it won't just ask you for h prime of 1. It might also ask you for something else. The other thing too is they want to make sure that you recognize when to use which piece. Because it's really easy to sort of skip over something and decide that you somewhere in there you're supposed to find f prime of 1. Or you're supposed to find some other piece of this.
Pretty wild.
Pretty wild. You don't need any function in order to do this. This is just an application flat out of the rule.
Our homework should be.
You have a couple of them on there like that. So, yeah.
Makes me